So now we're at part 3, moving through our review for our final exam, and we got to the point now where we're going to talk about force. And when we were in class, we talked about forces as something that is a push or a pull. And so if you push something or pull something, you're said to have applied a force to the object. So the important thing about a force that I want you to remember is that a force can, in fact, cause a change in the object's direction. So if you have an object that's moving, the only thing that's going to cause it to either speed up or slow down or change its direction is some kind of a force. Of course, if you remember from what we were just talking about with circular motion, in order to get an object to move in a circle where its direction is constantly changing, there has to be a constant force changing that direction. That's the centripetal force, and we'll talk a little bit about that a little bit later in the review. But for now, we just want to know that a force can cause an object to change its direction. Let's look at Newton's first law of motion. Newton's first law of motion is the law of inertia. So inertia is very important to know, and that's Newton's first law. Inertia is this tendency of an object to maintain its state of motion. In other words, if you have a rock and it's just sitting there by itself, it's happy to be a rock and sit there, and it's not going to move. It's going to stay at rest in the position of rest until some force comes along and acts on it. All right? If the object's in motion and it's moving, if you want the object to speed up or slow down or change its direction, then some kind of net force is going to have to work on it or act on it. So inertia, we said, big definition right here, is an object at rest tends to stay at rest, and an object in motion tends to stay in motion, and here's the key, at constant speed or constant velocity in this case. So it'll continue moving at a constant speed in a straight line until acted on by some net force. And if a net force comes along and acts on that object, it's going to change direction. Or it's going to speed up, or it's going to slow down. So that's what Newton's first law is all about. It's the law of inertia. It's the tendency of an object to maintain its state in motion, or state of motion. If it's at rest, it's going to stay at rest. If it's in motion, it's going to stay in motion at a constant speed in the same direction until acted on by some net force. So then we talked about something called the free body diagram. Free body diagrams. And what you do with a free body diagram is you draw your object and you draw all the forces that are working on the object or acting on the object. So here we have an object, and if we want to draw the free body diagram, we will show the weight. This is the force of gravity. So the weight is certainly, this weight is the force of gravity. I have a little trouble with the pen. I don't know how to change this thing. Wearing out the tip. Weight is the force of gravity. So weight or gravity is pulling the block or the box downward. And of course the ground is exerting a force upward on the block. So we called that, if you remember, the normal force is the force upward from the surface that the box was sitting on. If someone come along and try to push the box, we would label another force here. Perhaps this is the force F of someone pushing on the block. And this is how you do the free body diagram. Gravity is always acting downward. So anytime you see an arrow directly downward, you know that you can identify the downward force component, on the object as the force of gravity. Usually. Pretty obvious that, if we're drawing something like this in a free body diagram, that this component going down is the weight. All right. We're going to move into Newton's second law. So Newton's second law is the famous F that's the second law, equals ma. And this is the net force acting on an object is equal to the object's mass times the object's acceleration. This is Newton's second law, and it says that if we have some object here of some mass m, and we have a net force. Now, what do we mean by net force? Suppose I push here with a force of 10 newtons, and suppose you are on this side pushing this way with a force of 5 newtons. So my net force in this case would be 10 newtons is going in the plus direction, 5 newtons is going in the negative direction. So the net force is going to be 10 minus 5, or 5 newtons in that direction. If that's the case and I have a net force, then I'm going to have some kind of acceleration. So the moral of the story here is that if you have some non-zero net force, you will have an acceleration. Put a little star there because that's important. If you have a non-zero net force, you will have an acceleration. Let's take another example here. Suppose we have the same box of mass m, and I push here with 10 newtons of force, and you push this way 10 newtons of force. Then our net force in this case is simply 0, because I'm pushing 10 to the right, you're pushing 10 to the left. We've got a net force which is the total or the sum of all forces. That's what the net force is. The net force is the sum of all forces. So if we've got a plus 10 here and we got a minus 10 here, we got 0. So there is no net force. And lo and behold, in this case, the object won't move. So there will not be an acceleration. So you've got to have some non-zero net force acting on the object. If you do, it's going to accelerate. And that's what Newton's second law is all about. So to give you an example, if I say, okay, I have, well, let's take this guy as an example. We'll do it. Example 1. You want to find the acceleration that occurs in this situation, and we're going to say the mass is 5 kilograms. Now the SI unit for mass, SI unit is kilograms. We got to remember that, or units. SI unit, what's the SI units? Let's put up here. SI units for mass is the kilogram. For length, GTH, is the meter, and for time happens to be the second. All right, so there's the little sidebar up there. Know your SI units for mass, time, and length. And where are we? Down here. So we got kilograms. We want to find the acceleration. So we know from Newton's law that the net force is mass times the acceleration. Our net force, as we said in this case, if I go 10 to the right and you push 5 to the left, our net force is going to be 5 to the right, so it's positive, so plus 5 is the net force. The mass, we're going to say, is 5 kilograms, and we need to find acceleration. So for this problem, it's a very simple problem. The acceleration is simply going to be 1 meter per second squared. Remember to include your SI units for acceleration.